Hello, I am half of the Sudoku group. I'm Daniel Wahlberg. I'm here to explain some of the more intricate parts of the Sudoku presentation. So the first slide, or first, I want to tell you that for the history, just make sure that you understand the difference between a Latin square slash magic square and a Sudoku square. And I'll tell you the difference right now. Is that a Sudoku square follows certain rules. That is the digits 1 through 9, and it's an n by n square, so 9 by 9 square, and it follows the 180 degree symmetry. This is contrasted with magic squares, which are not necessarily 1 through 9, nor are they 9 by 9. And this is interesting because the French, who published puzzles in their quarter dailies, actually might have had 9 by 9 squares, but they call it magic squares, and not necessarily had these 1 by 9 or 1 through 9 digits and 180 degree symmetry. So we're going to go over the general form right now, which is really important to understanding what's going on in Sudoku. So as I said, Sudoku is a 9 by 9 square or n by n grid with 3 by 3 subdivisions. And then each row column contains the positive integers 1 through 9 without repeating, as well as the 3 by 3 squares without repeating. So what that's saying is that each row and column have 1 through 9. That's pretty simple. And then, as I said earlier, Sudoku carries with it a 180 degree symmetry for aesthetic reasons. So, as I say, if a given digit is in a cell XY, then there would be a given digit in cell 10x minus y, or 10 minus x, comma 10 minus y. So what that's showing in figure 1 is on just 2 slides ahead, is that if you have a cell, let's say A1, the corresponding cell is going to be I9. So it has like that 180 degree symmetry. I've never noticed this before. I know it, but apparently it exists. It isn't that every cell is going to be like this. It's basically like a crossword. A crossword also has 180 degree symmetry, but it carries with it. I've never noticed it. Obviously, it's not very aesthetic if I haven't noticed it through looking, but apparently it's there. It's not really that important to understanding. It's just kind of cool to figure it out. Like, hey, if I have cell A4, then it's going to correspond to I6, which is kind of interesting. Just showing how the 180 degree symmetry would work. So the general form that I've stated before, or I haven't stated before yet, but I'm going to be using it, and it's going to use the columns A through I and the rows 1 through 9, as well as subdivisions of random, well, not really random, but they are kind of random, Greek letters that kind of look fun, the ones that we use most often. And so we have alpha, beta, gamma. Is that gamma? I'll have to look that up. Gamma, delta, lambda, pi, sigma, phi, and omega. Just to show that, and just to keep them different from the columns and the row alphanumeric numerals, that's how I used it. There isn't actually a general form like this. This is what we're going to be using to denote the general form. So I'm going to be listing the cells that they I'm going to denote cells by column, row, 3 by 3 square in that order. So it's a coordinate. So it's going to be like A1 and then in subsquare alpha. or in this example, I used column C, row 3, subsquare alpha. So if we look at the solving math, or solving using math and logic, this is just an overview of what we're going to be doing, just some techniques, deductive and inductive techniques, and I'll explain how we're doing that as we go on. The puzzle we're going to try to solve is on the next slide. As you can see, there are many givens. It's a very easy problem. Not very easy, but it is easy. It's listed on easy on Sudoku.com. This is where I got it. I couldn't tell you the number because I didn't get the number. I didn't write the number down. It's probably in the millions or billions or whatever. Well, probably millions. So it's an easy puzzle, and there's a lot of givens. I didn't count how many givens there are, but there are a number of givens, which makes it easier. Not necessarily though. Well, it is definitely easier because of how many givens there are. There are a lot of givens, but the givens will determine the unique puzzle structure or the unique solution, and the givens determine how many Sudoku puzzles are possible, which is really cool. Alright, so possibility theory. This is the first one that we go through. It's a deductive theory, or deductive logic, using deductive logic. And it's just basically going through these propositions that are just given by the rules of a Sudoku square, in that the rows and columns and subsquares contain the digits 1 through 9, and this given cells already contain the solution digits. So what we can deduce from that is that it is possible that any cell can contain the digits 1 through 9. So if we had a blank 9 by 9 square, we could fill in the digits 1 through 9, or well, like we could list for each cell 1 through 9, and that would be right. Like the possibility would be in that cell. But if we take it further and we apply it to a puzzle that we're trying to solve, then the given cells are going to contradict the possibilities. So if I have a given cell of A1 being A2, and therefore all of row 1, row 1, they can't contain it won't be possible for them to contain the number 2. So it automatically strikes out all of the possibilities by the row, and then by the column too. So if I said A1 is 2, then column A, none of the other cells in column A can contain the number 2. As well as a square. It works very much the same way. And then the conclusion is that it is possible to deduce the cell's contents by eliminating all the possibilities. Again, comparing them to the givens and working there. And then once you get so far into this possibility theory, that you can work from what you already deduced from the rows and columns, and then applying those solutions to contradict the possibilities further. So there are many steps. You never really think about the steps that you take. That's what I learned from using this logical method to try to explain everything. But this possibility theory, I never use. I use it in a very limited way, and you'll see why. Well, actually, you can see why on the next on the next slide. So the next slide is the possibility versus rules and givens, and this is just going through the possibility theory, and you can see why we don't use it, because each square that isn't given, or each cell that isn't given, each cell that isn't a given doesn't have a given solution, I've given I've given it every possibility, 1 through 9, which is kind of ridiculous. And then, so for the first one, I went by, what did I go by? By the squares. So I looked at each of the squares, and I reduced number of possibilities by looking at the squares, by the 3 by 3 squares. So that what that's saying is that, like, say for I look at the given or the general form. Just keep the general form in mind. Let's look at delta, 3 by 3 squared delta, which is going to be covered by A4 through C6. So sub-square delta 7, 9, 2, 8, and 4 are already given. So therefore, the possibilities for C4, A5, A6, and B5 are going to be the possibilities excluded from those are by the givens. So 7, 9, 2, 8, and 4 exclude the possibilities of those digits in those remaining cells. So that reduces a lot of possibilities, as we can see, because a lot of the possibilities are given, or a lot of givens in sub-square delta. For the next one, we go by row. So we go by so like for row 1, we see that 8, 4, and 5 are given. So therefore, the remaining cells cannot contain the numbers 8, 4, and 5. So then we just eliminate those. Alright, so then on column, and then by column, and I just did the same thing, and just going through there. So you're going to skip a lot of this. And then I just repeated everything. So once we have givens as well, or solutions as well as givens, we can reduce it further. And just comparing the redundancies and taking out the possibilities. So what we're left with, I want to show this odd man out rule while I have the, while it's a possibility, or while I had the possibilities up. This is one of the limited uses of possibilities that I would use. So say for, say that I look at column A, I see that for the possibilities, number 9, or there's only one possibility of number 9, and that's in A1. None of the other blank cells contain the number 9. Therefore, A1 has to be the number 9 because it is the odd man out. It is the only one that has the possibility of being number 9. Therefore, it's number 9. And so we can't solve it, but going through this exercise, we really can't solve it by possibility. And you can see why, and it's kind of ridiculous to do it this way. And we got a number of them. I was very surprised how many we got out of this. But as you can see, we didn't get everything, and it took forever. Not on your part. It took forever on my part. And it would be very messy to handwrite everything in there. But as I'll show you later on, is that you can use possibility for counting as well as for just keeping everything straight. And that's a better way of marking in the possibilities of each cell. But it does work, and it shows you a lot of the logic behind Sudoku squares.